what is the minimum feature size. So you'll have heard that something about chips getting twice as fast every 2 years, or having twice as many.
6 months.
2 years. So most of that is driven by technologies getting smaller. So back when, in the 60s, when they were first doing integrated circuits, the smallest feature was maybe 100 microns across. And for the first 10 years or so, it got half the size every year. And subsequently, it's been doing about every 2 years, which is where the 18 months comes in, is because we did one and then the other. And people said, on average, except we've been doing the 2 years for a lot longer than we ever did the one. So basically, the smallest feature you can build on these technologies, we just publish as one number. So in this case, 40 nanometers. So, has anybody seen you've done electronics courses, you know about FETs? MOSFETs. So you'll know that when you're looking sideways, a MOSFET, we have a gate. Does that look familiar? Gate, source, drain. So we've got our channel in here. Also looks like that on a schematic. So typically the minimum feature size you can produce is this dimension here. So when I'm talking about 40 nanometer, that means the length of the gate, the smallest I can build is 40 nanometers. I can build them longer, and if you've done any work with FETs, you'll have played with the width, the length parameters. But basically this is the smallest thing we build. This dimension here across these is probably going to be about twice that. If I want to connect up here to a piece of metal, then that's probably roughly the scale, and as you get to the top layers, they might be 10 times wider than this. But we characterize it just on the one dimension and assume everything scales up from there. But so currently, the world, if you went out to build a product and you want, again, it's a cost thing again. So there's 180 nanometer, which people often write as 0.18 micron. You've got 150, you've got 130, 90, 65, 40, 28, and 22 is coming. Roughly root 2, if you skip 150 anyway. So that means you've scaled the linear dimensions by root 2, the area is halved. Hence, double as many transistors. Main thing you notice changing is that the transistors get faster. The parasitic capacitance is between all the various elements. The dimensions have shrunk. That enough of an answer for the dimensions? So, all about cramming more transistors on. So, I have a presentation here, but I'm not really going to stick to it. As I was saying to somebody here, we talked about the 3 levels, and most people work in FPGAs. few work in ASICs, very few work in custom, and then maybe a few more than, or somewhere in between the custom, actually work in analog. My main role is actually in analog design. I design, Perceptu's main focus is on SerDes, which is serializer, deserializer, talking maybe 10 gigabits per second across 1 meter of PCB trace. But next year we start thinking about 28 gigabits per second, but not until they give us 28 nanometer processors to work with. So this is slightly off topic for you guys in terms of digital, but it gives you a picture into the world of ASIC design that is easier to give this way than trying to go and talk about digital design that I don't really know a lot about. So this is an outline of a specific project, and I'll talk about some of the aspects of that. So one of the things that is happening as we move to the smaller geometry processes is the voltage you're allowed to put across a FET gets smaller. If you've worked with circuits, you've probably been given 3 or 5 volts if you've been analysing things, maybe even more. If you put 3 volts across a FET, then you create some sort of electric field, and the closer you bring them together, the higher the electric field gets, until the point where you simply can't turn it off. The electrons drive through. So as we get smaller, we've got to stay within physical limits. So a net result is that in 65 nanometer we might be allowed to use 1.2 volt supply. In 40 we get 1 volt. If we're lucky, in 28 we can probably still sneak out 1 volt. Everything on a chip, you're making a bunch of transistors, and you hope that every transistor is the same as all the other transistors that are laid out the same way, but they're not. We're down to the point, to give you just a picture, 40 nanometer, 60 nanometer, anybody got an idea of what the wavelengths of visible light is? Yeah, so 600-700 nanometers. We're talking 10 times smaller than the wavelength of visible light. If you went and remember your high school physics, where they told you the smallest thing that you can focus light on is the wavelength of light, they're wrong. These things use a photolithographic process, and every day millions of chips are turned out that only can possibly be done when they're focusing light down to 1/4 of a wavelength. Now, they're true in the fact that if you have the same pattern and you want it to appear at a projection, yes. So somebody's done a whole bunch of computer processing to produce the masks so that the interference pattern resulting from what they put on the mask when the light hits the wafer has feature sizes down reliably at the 28 nanometer level. But the net result of us operating at this small size is that statistics is breaking down. They say now that in the source or the drain, we're trying to make an N+ region by doping in specific atoms to give us that. If we got like a 500 nanometer process, there's a lot. Minimum sized transistor, we might only have 50 dopant atoms creating this thing. 1 or 2 change of the number of atoms you put in there and your transistor has changed. So the smaller we get, the more. So in a digital context, while talking about the timing, the delay through, say, some specific logic gate, that we can't just call that one number. If we've got transistors that are slightly faster, then that delay's gone down. Great. we can run it faster. If we got another one, it might run slightly slower. Now our timing's stuffed. So we have to make some assumptions based on what the slowest we're reasonably going to see. And then every chip is tested the moment it comes out, and they throw away 10 or 20% of them for errors that can't be controlled. Yeah, I won't worry too much about those other points. So, of course, the reason we're all going towards these smaller geometry processes, despite all their problems, is that we want to go faster. And I have actually manufactured silicon with hand-optimized logic running in excess of 12 gigahertz on a 40 nanometer process. That's standard CMOS structures that you would have seen. There are other things, if you want to look for things like current mode logic, CML, which is based on a differential amplifier with a lower swing and a higher speed. You can probably run it at 30 or 40 gigahertz in this process. But standard CMOS, we can hand optimize to 12 gigahertz, which is a hell of a difference compared to the standard tools that, like the ones you're using, that might be able to do 500 or 600 megahertz if you're lucky. We've reduced our parasitic capacitance, so our power goes down, and we've got higher density of gates, so we can fit more in a lower area. We've got lots of layers of copper. This process had 11 layers of copper. If you go talk to university mates who use the cheap processes that'll do a good deal for a university, they might have 3 layers of metal, which really makes hooking things up difficult. And we're going there because that's where our customers are. This is business after all. So the project I'm talking about is a PLL, which probably none of you have the faintest idea what a PLL is. Okay, a phase lock loop, PLL, is how am I going to describe this? It's a feedback system that we can use to generate a clock. So if the typical use of a phase lock loop would be to multiply a clock. So if I got a reference clock coming in at 25 megahertz, which is typical of a crystal, but I actually want to run my microprocessor at 3 gigahertz, which I guess is pretty typical in this day and age, then I somehow need to create a clock that is somewhere in the order of 100 times faster. Now, phase lock loop, we use an oscillator, which can be running at the 3 gigahertz. We can divide its clock down with our 100 down to the 25 megahertz level, and then we compare the phase. So we can check the timing between the edge of the reference clock and the edge of the divided clock and line them up. When every edge lines up, then we know the divided output of our oscillator is running at the same frequency as our clock, and hence our oscillator must be running at the divider times faster. Don't worry if that doesn't make sense. You might meet PLLs in fourth year. But, so our target was to meet the SerDes applications. We were running our serial communication at up to 12.5 gigabit per second, so we need a 12.5 gigahertz clock to make that happen. I guess you don't need to know about jitter. We have plans to use it in RF. The thing doesn't just run at one frequency, it runs at a range of frequencies, and we're trying to do the whole thing in less than 20 milliamp because our competitors use 50. Oh look, there's a PLL. For any of you that want to know, we have a phase frequency detector which compares the phase of these two signals. we run it through a loop filter, which basically eliminates the high frequency stuff and then does a little bit more. That controls the frequency of an oscillator. We divide the oscillator by the speed, and then we make these two frequencies the same. So this frequency must be n times 4 faster than that one for them to be the same. Or the two left-hand signals are the same. If I know the two left-hand, if you've done some control systems, have you done control systems yet in second year? Next year, okay. You'll all get to learn about the joys of stability and things that oscillate when they shouldn't. So, to address some of these challenges I've talked about. So, we actually want to minimize the amount of analog circuitry because the transistors in these technologies really are pretty horrible to work with. So you can make them do digital functions because that's only two levels that we actually care about the signal being in, and we don't care. If we're trying to do analog stuff, then it's got to have nice clean gain curves and the like. So we're trying to do as much as we can. So if I go back one page, in a traditional phase lock loop, the phase frequency detector is an analog block. The loop filter is an analog block with current sources, capacitors, resistors in it. The oscillator is an analog block. I don't know, you've met LC oscillators? Okay, we don't worry about that. So we've got three biggest parts, and then the divider's a nice simple little digital circuit at the end. In the phase lock loop we build on this process, we've replaced the phase frequency detector with a digital block. We've put in a DSP block that does the loop filter, all in digital, and the oscillator is still somewhat analog, but it's controlled by a digital signal. So we've tried to move towards being more digital because it suits no, none of that's relevant today. If you guys haven't seen LC tank oscillators. So here we're back on this, we're back more in the ASIC flow. So our loop filter, because that's only running at the reference clock rate, which is probably somewhere between 25 and 500 megahertz, it's slow enough that we can actually write it in our Verilog, synthesize it, place it as a block. That's a really good thing because you can use the same Verilog code, pick a new technology, recompile, and you've got the same block and now it does the same thing. The other blocks are where we start. So the phase frequency detector is custom digital because I care about the last 500 femtoseconds. The frequency divider is custom digital because it needs to accept a 12 gigahertz input. But the loop filter is slow enough that we can do with it. Skip that. Skip that. Okay, this is a chip layout which you may never have seen before, but the whole of the chip actually sits on the surface of the silicon crystal. We've laid down our transistors and various levels of metal. So what you can see here is a great big inductor in the middle. You can see our bond pads where we connect to the outside world. There's a voltage regulator hiding under there. This column is what digital logic looks like. It's a very regular structure because it's produced by the thing. This section's a bank of switch capacitors with some smaller ones just there. And then just above that we've got a little bit of custom logic that's running at our 12 gigahertz. And then this is just capacitance on our power supply. Oh look, I even got some. So some thoughts on the complexity of projects. So how many hours would you spend on Noni's project, even if he has made it difficult by putting it in NCL?
30k hours.
30k hours. How long is that in years? Okay, so 40 hours a week? You think you'd spend a solid week on your project, or is it bigger than that? Smaller than that? It's only a second year project. What's that? 10 or 20. Okay, so I'm out by an order of magnitude. So a small real-world project, 8 engineers for 16 weeks is 5,000 hours of effort. We're talking, going back to your 20 hours, about 250 times bigger. Yeah, that's about right. A real project, we're talking 30,000 hours. I'm quoting projects at the moment that are 10 times bigger than that. So once you move out of university and you've got the basics, the biggest task is how to make all the big stuff work together. How do you break down the project and mean that a group of 18 engineers on the right there can actually work together and produce a result that works all? It's hard enough to get your thing working as you think it's supposed to without trying to convince it to work together with the guy in the next bit. I'm not going to talk about that because you'll notice there's probably a number of engineering management courses on your program. Yeah?
Research into new technologies, what's leading that? Is it university researchers or is it private? Like who's funding that sort of research?
At the moment, industry. All the semiconductor journals, the best papers come from big companies. The universities have trouble keeping up because of the cost involved. But if you, going back to the technologies again, the 28 nanometer, that there are maybe 4 companies, maybe only 3 at the moment, that are actively trying to produce manufacturing lines to produce a 28 nanometer process. Each one of those will be putting in somewhere between $7 and $10 billion of research and buying equipment before they go to production. 10 years ago, we might have had 100 companies. Maybe 15 years ago, we might have had 100 companies that were in the manufacturing game. Now, high-end, 3, maybe 4. So your university can't keep up.
So is it like, it sounds like industry's doing one thing, and I'm wondering why we would be focusing on asynchronous.
Industry is working on asynchronous. But there is a lot of thought going in there. Okay, That's all I wanted to say out of that presentation. Are there any more questions for me on anything I've said? Up the back?
What stops the industry from jumping ahead of new generations? Why can't 10 years ago, why couldn't we produce a 22 nanometer chip?
There are a number of technologies progressing together.
Why can't we just use a small laser or whatever?
Well, part of it is that anything, if we want a 22 nanometer technology that's useful, then it has to be consistently. Everything working. You want to be able to churn out of a factory 1,000 wafers a day, which could mean like 1,000,000 chips a day. And 90% of those want to work. So finding out some way I can build, because people can build like a 5 nanometer technology transistor, but they can build one. And they might want to build 100 to make that work. So, and the other part was the one I just said to him, is it takes $7 to $10 billion to move from 40 nanometer to 28 nanometer. And the companies that are doing that, they can only just do it. So the answer is yes, they'd all love to go to 13 nanometer tomorrow, but they don't know how. More questions? Okay, no more questions. You can all escape.